Morning. Oh, thanks.
Well, 1 o'clock in this building.
Yeah, I hadn't even noticed it was.
Every spring and fall, I come through here and change them, and man, I'll tell you what, it takes a minute.
Yeah, it does. Well, I guess the clock change wouldn't explain no one being here, but morning. Section. So no, I'm not going to go over the exams. The only thing that there were, actually, since there are only two of you here, but a couple of things that several people missed. One is just the fundamental relationships that the divergence of the D field is equal to the charge density. So that's kind of fundamental, and that actually kind of came up in two problems, certainly one problem, and you could use that in a second problem. And then the other thing is with regard to, carrying out these vector operations, if you're given the field, scalar or vector field in, a certain set of coordinates, Cartesian, cylindrical, spherical, you have to use that defined operation from that coordinate system on the handout. Either that, or if you choose to use the Cartesian operators, which are certainly simpler, but then you have to convert the field over to the Cartesian representation, which is not simple. So that happened with a couple of people. So you just need to be careful there. Today I want to talk about actually some we'll continue our discussion of Ampere's law, and we'll look at a couple of classic cases for current flowing in a conductor and what the corresponding magnetic field is created. So the first case we're going to look at is a straight coil. And what does that mean? A coil is obviously has loops in it, but this is coil wound around a straight rod. Now, these coils may be wound around forms. The form may be some sort of magnetic material. It may be wound around forms and then the form removed. So they've got either an air core or a metallic core. So we'll talk more about this in just a second. But where we're getting to is we'll learn how to calculate the inductance of a coil from the magnetic field. So last time we talked about a straight wire aligned along the z-axis with current flowing up, and it's important to get the direction right here for the magnetic field. Magnetic field, loops around the current, and the direction is important with I directed up as shown here. The magnetic field would actually be, put your thumb in the direction of the current and then curl your fingers around the wire, and then your fingers then are pointing in the direction of the H field or the B field. So in this case, you're looking down from above, the magnetic field would be flowing counterclockwise. And the result we had there for the H field was when we assumed our wire had a radius A, and so when the radius to the field point was inside the wire, the magnetic field increased linearly with rho. Outside the wire, which is where we typically measure the field, the magnetic field intensity decreases with that radial distance. So it falls off to zero the farther away we get from the wire. And take note of the right-hand rule relating H and I, because it's going to be important as we work with these coils to get the magnetic field correct. Now, also, I'm going to try and draw a coil. It turns out it's important to get the winding direction correct, or to talk consistently. So I can't just draw a loop. Okay. So what I'm drawing here is, I'll draw it this way. Usually makes it clear where, I've got this coil. And it's wrapped so that the turns are coming out of the board at the top and going into the board at the bottom. Okay. And we could certainly wrap it in the other direction, but I've tried to draw that here so it's clear how the coil is wrapped, because that actually will determine the actual direction of the field. And so, of course, the other thing that determines that is the direction of the current. So both those come into play, the direction in which the coil is wound and the direction of the current. Now, the way I've drawn the current here, with the current flowing, it would be flowing like this through each of these little segments. Now, also, you guys have probably seen inductors. And typically, inductors are wired very close together. It looks, by the way, you've seen inductors perhaps around with, they use a special wire, it's called magnet wire. It usually doesn't have, it's got a very thin insulator over it. It's usually clear insulator. So it looks maybe like pure copper, but it's not pure copper, because pure copper would short itself out and adjacent loops. So there is insulating material around the copper. It's called magnet wire. I'll try to remember to get some out of the stock room. But you can use that to wind your own coils or inductors. But now if you place your thumb along the current direction here, on the loop that's in front, notice that the H field would be directed to the right. And then on the loop that's inside in the interior of the coil. And then on the loop in the back, if you place your thumb in the direction of the current, again, inside the coil, the H field would be directed to the right. So here's H. And again, that takes some visualization to see that. On the wire in front closest to me, I put my thumb in that direction. My fingers are curl inside the coil. The H field would be directed to the right. Now, outside the coil, the H field would actually be directed to the left, right? Because they form loops around the coil on both sides. Okay. So outside the coil, if I put my thumb in the direction of the current again, outside the coil, my fingers are pointing to the left. But on both the front and back side of loops, as a matter of fact, as I go all the way around the loop with my fingers inside the coil, the H field is directed to the right. So we get an intense H field inside the coil. The loop actually magnifies, intensifies the H field, and that's why we create the coil loops, actually. We'll get a much stronger H field than just with a straight wire, for example. So this is what I mean by a straight coil. We'll look at some other cases, in particular, another common case is where the coil is wound around a circular form. It's called a toroid, or a donut shape. It's another classic configuration for a straight coil. Now these pictures are hard to draw. And again, I have to be careful with the geometry here. The other thing is, if I had drawn the coil in the opposite direction, so that actually, and I'd have to do that. I know if I change the direction of the current, the H field would change. I change the direction of the coil. So on the back side, it's now going down, then the H field would be in the opposite direction. But again, that requires some good visualization. But if I change, this is why I try to be really careful with how I drew this, but if it were wrapped around, so it came out of the board at the bottom and wrapped around, then the current would be flowing and that up, okay, in front, and then as I curl my fingers around, the H would be in the opposite direction. Or if I reverse the current, the H field would be in the opposite direction. So the field direction depends on both the current and the winding. The other way that you'll see this drawn, which I can draw a little more quickly, is I'll show, the circles here representing the wire. Okay. So this is like a cross section through the coil. And I'm not drawing all the circles. And then we show the current direction through the coil. It's shown with either a cross, and this is supposed to represent the tail feathers of an arrow going away from you. So that means the current is flowing into the board here at the bottom, because this is the picture I want to see, right? I want to see the arrow going away from me. We can show a field coming toward me or a current with just a point. And so this is supposed to represent the tip of the arrow coming toward me. So, on one side of the arrow, I see the tip, that's the small dot. On the other side, I see the tail feathers, that's the cross. So this means, so again, from this representation, which is, I don't have to be as careful with how I draw the coil, but now, with the tip of the arrow coming toward me, so my thumb out of the board on the top, wrapping my fingers around the wire, the H field is directed to my right. And at the bottom, again, with the arrow going away from me, my thumb going into the board, inside the coil, my fingers are going to the right. So I get an increased H field. Again, what really happens here is the H field does, and the B field does that. So you'll see this in a lot of this notation used in a lot of textbooks, not only for current, but it can be used to show the out of the direction of a field. So this is the tip of the arrow and then into board for the tail. And so this is an arrow tip tail drawing. So now that we've got the fundamentals kind of out of the way, the notation, graphical notation here I'm going to use this notation to represent a coil, the current flowing into the coil at the top, and flowing out of the board at the top, flowing into the board at the bottom with the tip and tail. And again, the other thing you'll see is typically in a lot of inductors, this thing will have multiple windings with the windings on top of each other. Okay, not just side to side as I've drawn it, but you'd have a bunch of wires actually here and stacked on top of each other, all with the current coming out of the board at the top and flowing into the board at the bottom. And again, because of the cylindrical symmetry here, typically, we'll use our center of symmetry as our z-axis. And so the length of the coil goes from Z1 to Z2. And I'm going to pick, remember in Ampere's law, I have Ampere's law says that the H field integrated around the contour is equal to the current enclosed in that contour. So I'm going to pick this as my, doesn't include the whole coil. Okay, so here's my contour C. I'm going to have 4 sides on it, S1, S2, S3, and S4 here. Now, notice my contour is not including both sides of the coil, because if I did that, the net current actually coming through my contour would be 0. So I don't get any information from that. So I just set it up, again, it's a virtual contour, set it up so that I just, it just includes the conductors on one side of the coil or the other. Now, this distance to side 1, that radial distance is ρ1, and the distance out to the other side is ρ2. And then I need, I'm sorry, Z1 and Z2 are not the length of the coil, but rather the length of my S1 and S3 sides, Z1 minus, or Z2 minus C1. Actually calling that length L prime, and the length of the entire coil is L. So this picture is showing my integration path. And this is a classic case, a classic problem where once we solve this problem and find the H field inside the coil, we can use it in a lot of different applications. So this is Ampere's circuital law, which we looked at last time. It says now the H field, my H field here, remember, is, as I've drawn it, I've tried to convince you, everywhere inside the coil, the H field is directed to the right. So here's where we have to bring in some symmetry. This is always necessary when you're using these integral forms. The H field is Z directed. Now I will allow it to be a function of ρ, the distance from the Z-axis. We could see, we've already seen that the intensity can vary the farther we get away from our center axis. But I'm assuming this thing is so long that the H field doesn't depend on the value of Z here. That won't be correct at the ends of the coil, where my loop, where these things start to loop around. But inside, very long coil operating somewhere away from the ends, my argument is that H doesn't depend on the distance along the coil. Of course, that's not true when I get near the ends of the coil. But I'm trying to find the H field inside. And then the other thing is I'm arguing that it doesn't depend on, the phi angle would now be, this angle around my Z-axis, and that I'm arguing it doesn't depend on phi either. Okay. by symmetry. And so because of this, H dot dl is 0 along S2 and S4. The sides of my contour, which are vertical, which are row directed. Okay. So they would actually be rho hat v rho, but when I dot that with my H field, I would get 0. And then I'm going to do a little trick here. I'm going to let rho 2 go to infinity. We can argue that H is equal to 0 then along S3. So the assumption goes that, here I've got this result that the farther away I get from the wire, my H field decreases with distance. So I'm going to say, S1 is a distance rho 1 from the center of my coil. But I'm going to let rho 2 be on my outside contour, be a long distance away, so the H field there outside the coil would be negligible. And so my contour integral, the left-hand side of Ampere's circuital law, just becomes this integration along S1. So from Z1 to Z2 of my H field is Z directed. It can depend on rho. And then my DL here is just Z hat DZ along S1. So I'm integrating in the direction of my field. The other thing that you remember, I have to pick my direction of integration to be consistent with the current, otherwise I have to throw in a minus sign. And then, so if my fingers are in the direction of the contour, my thumb needs to be pointing in the direction of the current, and it is here. The current's coming out of the board toward me. On the bottom, I need to integrate in a clockwise direction, either that or throw in a minus sign into my equation. So, but this integration is just over Z, and I've made the argument that H doesn't depend on Z. The integration from Z1 to Z2 of this constant, I'm going to get just Z2 minus Z1, which is L. So the result here from, it's L prime, that's what I called it in my figure, the distance from Z1 to Z2. So the left-hand side of Ampere's circuital law just gives me H times L prime, the distance of the path. Now the right-hand side, if there are n turns along L, and this is something we would have to know is, whether there's 1,000 turns in the coil, or 500 turns, or 240 turns, that's the number n. And then the other thing is we need to know the length over which those turns are wound. Then we can define the number of turns n prime along L prime would just be n over L, which is the winding density times L prime. Okay. So essentially that's saying if I've got 1,000 turns over 10 inches, how many do I have over 1 inch? 1,000 turns over 10 inches would be 100 times 1. I'd have 100 turns over 1 inch. Okay, right? So that's just a geometrical argument. Because what I need is the number of turns inside this contour, and that's n prime. Okay, just from a geometrical argument. And so the total current flowing through my contour then is n prime times I. I've got a constant current I flowing through each of these, or N, L, L prime, I. Finally, back to ACL, equating the two sides, I've got H rho L prime is N L L prime I. And so I cancel my L primes. H rho then would be Ni over L. And plugging back into my formula then for H, my vector, then, and I finally get the result I want. It's Ni over L. Or for the magnetic flux density, it's mu H would be U N I over L. Again, if the center of the inductor is air, we say it has an air core. The core of the inductor or the coil is air, then mu is equal to mu zero. But if it's some magnetic material, its mu will be greater than mu zero. Sometimes many times greater than mu zero. So we get a large magnetic flux density by using a magnetic material inside the coil. Notice here that, remember, the units for H are amperes per meter. So again, we have that I here is amperes, L here would be a distance in meters. So, and then N is unitless. It's a number. So the units are correct. But let me just make a note. The field inside a straight coil is uniform. That means the field intensity doesn't vary, it's constant, right? As long as the current is constant. And proportional to, it also means, I started out with this assumption that I was allowing the H field intensity to actually change with rho inside the coil. Well, we found it doesn't depend on rho, it's constant. I allowed it in the assumptions, maybe be stronger toward the center and maybe get weaker as we got, or vice versa, have some dependence on rho, but it doesn't. It's constant everywhere, and it's proportional to the winding density, which is N over L, and the current. And we'll come back to this result. We need to do a little more work. We're going to look at a couple of other different shapes and calculating the H fields for a couple other different shapes, but we'll come back to this and use this result to calculate the inductance of the coil. Okay. Another classic shape is what's called a toroidal coil, where here, again, I'll try to be careful about how I draw this thing with current going in here. So like this, and usually we'll typically have a lot more loops than I'm drawing. Okay. So from that picture, use the right-hand rule on the individual wires to determine how the direction of the H field inside the toroid or the donut. Is it clockwise or counterclockwise? Yeah, so thumb in the wire now, I'm curling my fingers, on the back side of the front because I want the direction inside the toroid. It's different outside, but inside it's going to be directed counterclockwise, right? So, and that would be true on the back. On the back side, I put my thumb in the direction of the current, but my fingers inside the coil, it's still directed counterclockwise here, all around my coil. This would be H, based on the direction that I wound the coil in the direction of the current. If I reverse either one of those, okay, then the H field would be in the opposite direction. Okay, the tip tail diagram, which is easier to draw, notice current going into the board on the outside of the donut. So that's where my X's would be. And then coming out toward me on the inside. There again, I can use this picture, with on the ones coming toward me, the H field would be in that counterclockwise direction here. Now, haven't actually talked about, and it's certainly not at all obvious from the pictures I've drawn, that the cross section, now I don't mean a cross section through the toroid like this, but if I sliced it in half like into the board, we might see it could be actually, a rectangle. Okay. It could be a true donut shape. Okay. But if we could have a different cross section. You'll see both of these actually in practice used to wind inductors. Okay. So here, if I've got my current loops like this, I like that, okay, wound around the inductor. Again, H would be actually coming out of the board at the top and then into the board at the bottom. So this is I, this is H. So I use that tip tail, the previous diagrams, to represent the direction of I, okay, but now I'm using it to represent the direction of the H field. Again, it's going away from me, flowing around as I've drawn the current. It'd be the H field would be flowing into the bottom of the toroid and coming out the top. So for our assumptions here, we say that H is, let me actually add in a coordinate system, X here and Y, keeping with our convention that our axis of symmetry, or Z-axis for cylindrical symmetry, then would be coming out of the board towards you. Okay. So the angle phi is measured, remember, counterclockwise from the x-axis. So H is phi directed. I'm going to say now it could depend on rho, and it could depend, and so rho would be this radial distance. And it could also depend on Z, the height above the XY plane. And again, that's where the cross section actually may come into play. Because my cross section changes as Z increases. Here's my x-axis at this point. Or y-axis. And then DL now is phi rho d phi. I'm going to do here's my integration contour, and it just encloses the current in the center of the toroid. And then so H dot DL is 0 to 2 pi rho H rho Z d phi. Fortunately, I'm integrating over phi, and by symmetry, I've argued that H doesn't depend on phi, so I just get 2 pi rho H rho Z. The current enclosed is, now I don't have to worry about the current density because my contour includes all the loops in the coil. I've got N loops inside, N loops outside. So N times the current I. So from ACL, I've got 2 pi rho H rho Z is equal to Ni, which leads to H rho Z is Ni over 2 pi rho, and H then is Ni over 2 pi rho. This is inside the coil. And B is mu H, would then be phi U Ni plus 2 pi rho. Outside the coil, H is 0 actually, because with our contour, there's no net current actually enclosed. Inside the coil, H depends on N and I, and now it doesn't have actually a uniform strength. It's stronger toward the center of the coil and gets weaker as we go outside. That's primarily because the winding density is smaller at the outside of the coil because it's got a longer circumference there. And then the other thing is we've got the same result here, so the cross section never came into play. So it's the same result for either the rectangular cross section or the circular cross section or some sort of oval. That doesn't actually come into play in the field strength. There's one more classic case that we want to look at, and this is the current sheet. It doesn't seem very realistic, but it can actually be used to model the ground plane on a printed circuit board. And so here's, I'm going to lay out my coordinate system here with Y and Z. And here, modeling this as an infinite current sheet with showing which way is the current into the board or out of the board. Out of the board, because the tips of the arrows are coming toward me. Okay, so I'm in trouble. So, and then here's my and again, my contour integration would be counterclockwise to be consistent with the direction of the current enclosed. This is distance Ly, and then the Z distance I'm calling Lz. And here, I'm going to model the current as a current density, a surface current density. So the surface current density here is actually, so X would be coming out of the board, and I'm calling that just JS. And it would have units of amps per meter. So ideally this would, if I have you could think of a wide rectangular structure, passing an amp of current. The amp of current there would actually be the current density would be the amp of current divided by the width. I'm saying it's infinitely thin or very thin rectangular width. We could talk about the current per area. The current enclosed then is just the current density times the length of the structure. And again, I have to use a symmetry argument. These are always a little bit sometimes hard to buy, I know, but we can they've been verified through measurements that these theoretical results and these assumptions give us measurable results, or results that agree with measurement. Now, we get that with this current sheet, an infinite current sheet, that the H field, the current coming out, the H field is actually going to be going in the negative Y direction above the Y axis here. And it will be going in the Y direction below my Y axis. So it's Y directed, it'll turn out for Z positive, H of Z will be negative, and for Z negative, this will be positive. But it's odd, okay? And that's what this relationship is saying. It's equal and opposite above and below the plane. And I'm allowing it to have a variation with Z, a distance away from the plane, but no variation with Y, because it's infinitely wide and it's infinitely long, so no variation with X either. So contour integral is from minus Ly over 2 to Ly over 2 of H along the bottom. That's minus Lz over 2, but I'm integrating along Y here, and then along the top, it would be Ly over 2 to minus Ly over 2, and then my H field is Lz over 2 dy. And so this actually becomes, so this is a constant, I can actually pull it out. My integration is actually going to give me Ly here and minus Ly here. But these two functions are equal to each other but opposite in sign. And so what I get here is minus 2H Lz over 2 times the length Y. And from ACL, I get this result, Lz over 2 Ly is equal to the current enclosed, JS Ly. So fortunately my Ly's cancel, and I get H Lz over 2 is minus JS over 2. Okay. Now this is actually independent of LZ. It doesn't depend on LZ or Z. So finally I get, putting all the pieces together for my H field, I get minus Y JS over 2 above the plane and JS over 2 below. The minus sign again is just accounting for the direction of the field. It's negative Y directed above the Y XY plane, and it's positive Y direction directed below. And if I'd shown the current actually going into the board, those signs would have changed. So you have to keep that in mind. What's a little surprising here, although we had something similar for the electric field with an infinite sheet of charge, is that the H field doesn't get any weaker the farther we get away from the plane. Okay, and again, this is a theoretical result. We're assuming that it's an infinite plane. In practice, we don't have infinite planes, and the farther we get away from any current carrying rectangular strip, the field would get weaker, but it's a good approximation if you're close to the current carrying plane, okay, that the field doesn't weaken with distance until you get far enough out from the plane that the other dimensions become important. But as long as the distance from the plane is small compared to either the width or the length of the plane, this is a good approximation. The field is just equal to actually the current density. Now, in some of the problems, we can actually use superposition. You may have two separated planes with current flowing in one direction and one, and the other direction and the other, in which case you get a stronger plane in between equal to the sum of the two. And then there would be actually, again, no H field outside the two conductors. Let's see, I did hand back the exams. If you want to talk about the exam, please come and see me in my office. If you have any questions, because I did make a lot of comments on mistakes I found on the exam, but come and see me and we can discuss it. The other thing, I make sure that you meet with your advisors. Seniors would actually start registration today. Juniors start Wednesday, perhaps. Yes. When is it?
It's tomorrow.
Tomorrow? Okay. You guys would know. I don't really know. Juniors start tomorrow. Have seniors already started? Or is today the first? Seniors start at 2 today. Okay. So make sure you're ready to go there. All right, that's it.